Alright, so this is chapter 24 of organic chemistry. So some organic terms, we've got a functional group, and that's a group of atoms largely responsible for the behavior of the molecule. And hydrocarbons is a hydrocarbon or hydrogen molecule, and aliphatic does not have a benzene group, and aromatic has a benzene group.
General formula for an alkane is CnH2n plus 2. So in other words, if you know how many carbons you have, like 4 carbons, then you take 2 times 4 plus 2. Butane is C4H10, would be the general formula. Alkane is referred to as a saturated because it's the maximum amount of carbon-hydrogen bonds. If you've ever heard the term saturated fats, well, that's a long carbon chain without any double bonds because then you have the maximum amount of carbon-hydrogen bonds there. Structural isomer is the same formula but a different structure. So again, I could give you C4H10, and if you remember your organic chemistry, butane would be that 4-carbon chain. We could also give you 2-methylpropane, which would have the exact same formula, but it has a different structure to it. Now, naming rules that we have to remember is 1, you have to identify the longest carbon chain. Next, the alkyl groups are numbered and alphabetically listed. So if we go over to the board, we'll give you a couple examples here, beginning with, and I'm going to draw this out in what we refer to as line angle format, 2-methylpentane. So again, first of all, I guess I'll write down 2-methylpentane. If I draw it out in the normal organic, or the normal, Lewis dot manner, I'd first draw out a 5-carbon chain, 1, 2, 3, 4, 5. On the second carbon is a methyl group. A methyl group is CH3. Then after that, I just fill in hydrogens to make it at the octet. Because again, this is a saturated hydrocarbon. Now this is the Lewis dot way to draw it. We also taught you in Chem 2 what's referred to as the line angle format, a much quicker way to draw it. If I put my pen down, here's 1, 2, 3, 4, 5 carbons, and there's a methyl group. Now this is called 2-methylpentane. But what if I move the CH3 over here? This would still be called 2-methylpentane. The reason being, pentane is 1, 2, 3, 4, 5, still the longest chain, but you do your numbering then, the 2 part, based off of where your functional group is. And in this case, I would start numbering 1, 2, 3, 4, 5. So even though I moved my methyl group to the other side, it's the exact same problem. Now when we say structural isomer, a good example of that could be if I had a 3-methylpentane. So 2-methylpentane and 3-methylpentane would be different for their structure. Another example I want to give you is 2,3-dimethylhexane. So 2,3-dimethylhexane. And from now on, I'm going to stick to just doing line angle format to make it go quicker. Whenever you do a problem of drawing it, I would first draw out the carbon chain. So 1, 2, 3, 4, 5, 6. On the second carbon, I have a methyl group. On the third carbon, I have a methyl group. Again, di means 2 methyls. How you draw this out is always working backwards of 6-carbon chain. 2 methyl groups, where are they? One's on the second, one's on the third carbon. Some students don't like the fact that we could change this to a different problem of 3,3-dimethylhexane. If it was 3,3-dimethylhexane, I would have 2 methyl groups coming off of the third carbon. Again, here's the first carbon, second, and third. They think it's kind of redundant to say 3,3 and dimethyl, but once again, the naming usually work backwards. I mean, first identify the longest chain. What are my functional groups? Where are they located? Let's give you 2 more. One would be 4-ethyl 3-methylheptane. So again, 4-ethyl 3-methylheptane. I'd start by drawing the heptane, which is my 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. On the third carbon, I have a methyl group. 1, 2, 3. On the fourth carbon, I have an ethyl group, which is a 2-carbon functional group. Now, some students will say, why am I doing 4 before 3? I have to do my numbering based off of functional groups. And 1, 2, 3, 4, or 1, 2, 3, 4, this is always going to be carbon number 4. and this is 3. By alphabetical order, E comes before M is how I then write out the written name of it. The last example I want to give you in this slide of just a normal carbon chain is going to be something other than just the carbon groups on it. So 3-bromo, 2-methyl pentane. If I do my pentane, that's 1, 2, 3, 4, 5. On the second carbon, I have a methyl group. On the third carbon, I have a Br, or a bromine. So these are several examples of how to do alkanes. And again, keep in mind, an alkane is single bonded carbons with hydrogens all around, and they could have functional groups on them. The next slide goes over cycloalkanes. So still alkane, meaning single bonds. Cyclo means it's going to be a ring. The general format of that is CnH2n. Give you an example here on the whiteboard of how about cyclobutane. Cyclobutane, but is the prefix for 4, so I know the formula is C4H8. Cyclo means it's in a ring. Here's my ring, and then if I add hydrogens around to get to the octet, you can see that it's C4H8. By the way, if I were to do the line angle drawing for this, all I'd have to do is draw a square. 1, 2, 3, 4, there's my number of carbons. So cycloalkanes, not too tricky. Let's move on to alkenes. Alkenes have the same way of figuring out the formula, but now there's a double bond involved. They're referred to as unsaturated hydrocarbons because they do not have the maximum amount of carbon-hydrogen bonds. Cis-trans isomer is a good example of this. So if we go back to the board, if I had carbon double bonded to carbon, let's say I have a chlorine group on both of them. There's two ways I could draw it. I could draw chlorine like this, or I can draw chlorine, hydrogen, hydrogen, chlorine. Notice on this top example, the chlorines are both on the top. They're on the same side. This would be referred to as a cis for the isomer. This is they're on the opposite ends. This would be referred to as trans when the two are on the opposite end. So that's a simple example of cis and trans. And again, if I drew it out in line angle format, what I would have for cis is a double bond. Here's a chlorine, here's a chlorine. Trans would be chlorine and chlorine that way. So either way, there's your cis and trans. I want to give you one more example of this, of 4-methyl-2-hexene. 4-methyl-2-hexene. Now the 2 is indicating where the double bond is located, because when you see it end in -ene, you know hex is a 6-carbon chain, but now there's a double bond on the second carbon. So if I start off with, here's 1, here's 2, there's going to be 3. I'm going to do the cis version first. So here's 3, 4, 5, 6. There's a double bond on the second carbon, 1, 2. On the fourth carbon, 1, 2, 3, 4, is a methyl group. This would be cis, so we could call it 4-methyl-cis-2-hexene. So the cis would usually go right there. If I wanted to draw the trans version instead, I would do 1, and then this version instead, what would be an easy way to do it is 2, 3, 4, 5, 6. And again, on my fourth carbon is a down. Notice that here you have up and a down off the double bond. So this would be 4-methyl-2 or 4-methyl-trans-2-hexene. Again, on the top version, both groups are going up. Because remember, this is a hydrogen here. It's a hydrogen there. Here's a hydrogen. Here's a hydrogen. So trans is opposite ends. Cis is the same end. So the chlorine example was a simple version that you'll typically see. This is a more complicated version. If we move on, alkynes are going to be triple bonds. To figure out their formula, oh, sorry, went too far. To figure out their formula, it's going to be CnH2n minus 2. An example of alkyne, which once again is a triple bond, is going to be, how about something like butyne? So we could call it 1-butyne. This would be 1, 2, 3, 4 carbons, because it's 4 carbons. 1 butynes on the first carbon is the triple bond, and then you'd have hydrogens all around. If I did the line angle for this, that'd be 1, 2, 3, 4 for my number of carbons otherwise. So either way, we'll show you 1 butyne. That just involves a triple bond. If instead I called it 2 butyne, my triple bond would be on the middle carbon instead. I can't call it 3 butyne because if the triple bond was here, I would start numbering in the opposite direction. It would once again be 1 butyne. Two more things to go over. The first one is the aromatics. So once again, we covered all of them that are not rings so far. Now let's cover the things that are rings. Benzene ring is an example. One of the things that we did not talk about was ortho, meta, and para when it comes to a benzene ring. So first off, if you come back to the board here, what a benzene ring would look like is a 6-carbon ring, and we usually represent it with double bonds every other. I have seen it otherwise with a circle in the middle. It's something we talked about as a resonance structure. Now, if you have 2 groups on it, let's call this the first carbon right here. Let's say I have a group on the first carbon. Instead of calling it 1, 2, if I have a group on the first and the second carbon, instead you would call that ortho. If I had a group on the first carbon and the third carbon, it would be called meta. And finally, if I had a group on the first and the fourth, it would be called para. Now, we didn't discuss those where functional groups, again, say it's a chlorine on both. So again, this would be the para-chlorobenzene ring. We didn't discuss this in Chem 2 because I wasn't certain if that's something that you need to know, but at the same time, we might as well go over all of them. A very last slide goes over all the functional groups, and we'll just stay on the board here so I can show you an example of each. The first one is an alcohol. An alcohol is an OH group. Oftentimes in organic chemistry, the capital letter R represents that carbon chain. So an alcohol would just end in OH then. Ethyl alcohol would be an example. Ethyl alcohol is going to have 2 carbons to it, so C2, then it's going to be H5, and then an OH. Ethyl alcohol can also be called ethanol, so an OL is often referred to with the alcohols. And ether, a good example there would be diethyl ether. But how we would show that in general is you have a carbon chain, an oxygen, and another carbon chain. Remember, with that oxygen, there will be 4 electrons on it disposed. Diethyl ether just means we have an ethyl group, a C2H5, on both sides there as well. An aldehyde is next. An aldehyde would have some sort of carbon group on one side, double bond oxygen, and then hydrogen on the other side. So that could be a CH3, it could be beyond that, but this would be an aldehyde. Ketone would be replacing this hydrogen with another carbon group. So a ketone, we draw something like that. Here's an R group, here's a second R group with the carbon double bonded oxygen. Carboxylic acid, what it's going to do is replace that H or that R with an OH. So again, this would be the carboxylic acid group right there. Ester is going to be the second to last. What we're going to do is replace the H on the OH with another R group. So this would be an ester. The last one is an amine, like amino. So amine, you'd have your R group and it's bonded to NH2 to wrap things up. So again, if we go back to the slide here, these are the 6 functional groups, 1, 2, 3, 4, 5, 6, 7, that we have to be aware of. And as far as I'm aware of, you have to be able to identify them. Don't worry as much about naming them as you should be able to name the long carbon chains, but you should be able to name them. And that is the last lecture for AP Chem Review.